Hello students. The next part of this topic is in the semiconductors and electronics PN junction diode. Previous class we discussed the p-type metal, n-type metal. In p-type metal, holes are magnetic carriers, n-type metal is electrons are magnetic carriers. And in p-type material, holes majority, electrons minority. In n-type metal, electrons majority carriers, holes minority carriers. And minority carriers don't exist at low temperatures. Only at high temperatures minority carriers exist. Next, in this diode, what we are using is a diode. Di means two here. Ode means what taken from the electrodes. The semiconductor having the two electrodes connected. This one connector, the electrode is connected only making the connection from the battery and making the current to pass through. These two conductors are connected. It's called as the diodes. If you have the three connected, it's called the triode. Similarly, we have the diode, triode, tetrode, pentrode, like that. Different type of connections are there, but different number of connections based on. Here we discuss is only diode, and that two having the two type of metal, p-type metal and n-type metal. Two it's made as a single crystal bar, not separate keep in contact. We take the two crystal bars. One is the p-type metal, another one is the n-type metals. Combined, we can consider this as the equivalent diagram. Equivalent diagram p and n-type material, like we are taking the p-type material, p-type impurity. The material crystal bar is made and it is put into the molten metal of n-type material. Just touch and remove it, take it out. So what happens? The molten metal will come out along with this p-type metal attaching this. Melting is required with the atoms because one type of metal atom should be diffused into other type of metal atoms as a single bar. So p-type and n-type metal are made as a single crystal bar. In the p-type material, holes are the magnetic carriers, n-type metal, electrons are the magnetic carriers. We are discussing only magnetic carriers points of P now. So the n-type material, electrons are magnetic carriers. Whenever the p-n junction diode is formed, freshly formed, then what happens is electrons which are more in number in n-type metal will migrate towards the hole concentration mode. That means towards p-type. These electrons go towards the p-type. So electron going to the combine with the hole, then hole and electron both will disappear. Hole going here and combine with this electron going and combine with the hole, and this hole will disappear. The result is ion created. Losing one electron here. Previously with the electron only it was electrical neutral. With hole only it was electrical neutral. This is a p-type material. With the trivalent impurity, n-type material with the pentavalent impurity. So electrons is outside the bond only we are discussing here. But if both are electrically neutral only. Electron will go from n-type material to p-type material, and the hole and electron will disappear. But what happens here is this n-type metal will be losing the electron, it becomes positive ion, losing the hole it becomes equal to negative ion because it already neutral gain one extra electron, which is the bond, close the bond. Same thing happens at the junction. The electrons are going from n-type to p-type. We can say holes are going in the opposite direction, p-type to n-type, but actually it is electrons which are jumping. In this direction, holes are not crossing. Electrons only going in this direction. But generally we talk about the hole traveling in opposite directions. But here holes are not particularly n-type. Here holes are disappeared, here electrons are disappearing only. So we talk only electrons are migrating from n-type to p-type. Then what happens at the junction? Here the junction what is formed is called as a ions formation. This is called as a depletion layer. Depletion layer. Deplete word taken from deprive, means not present, like it is do not contain any living things much. At least like that. So this area is called as the deprived of the free charges. Means holes and electrons are able to provide the current by moving. So we call it the free charges. So that in this case, in this region, there is no free charge, so it is called the depletion region. And p-type materials, what type of the ions formed is negative ions. N-type metal, what type of ions formed are the positive ions. So this side will the negative voltage, get the positive voltage. Because these two terminals between these two ionic regions, in this ionic region, the potential difference is produced, that is called as a barrier potential, BB. BB is called as a barrier potential. It is produced between the ions present on the p side and the n side. P side, positive side, what is actually present is negative ions. N side, what ions present is called as a positive ions. Reverse this, careful with that. And barrier potential voltage is produced because between these two ionic regions, this is a depletion layer contains only ions. What is the ionic region? Ionic ions do not move there, the atoms only losing and getting extra electrons. Losing one electron and gaining extra electron. So these ions do not move. Only charges can move. Means electrons with light particles. Electrons are holes only in motion we can say to produce the current. So this area do not produce the current. Initially, electrons are transmitted from high number to low number, more concentration to less concentration. That is called as a diffusion current. Diffusion is the difference in the concentration, sir. And in the conductors, when you apply the battery potential, across this also, when you apply the battery, electrons collide with the atoms, the average velocity of is called as the drift velocity. The drifting happens in terms of the external force acting as the electric field. With electric field, the current is called as the drift current. Without electric field, because the concentration, different concentration of electrons, the current produced is called the diffusion current. But this is only temporary take place. Few seconds only, just fraction of a second it happens, electrons go here and ions are formed here. Thereafter, more electrons will try to go. Other electrons try to go here with some millions of atoms are produced here. I mean the ions. These electrons will try to go further, but these negative ions repels the negative, and similarly we can say positive pole is repelled by pole. These positive ions at the junction. So few initially migration takes place, but the charges after that stops, and more concentration of the charges. The doping concentration is more for this n-type p-type means more charges can flow. The reason what happens is the barrier width changes. More concentration, less is the barrier width. And then because the barrier potential electricity is produced, the barrier width is in the order of 10 to the power minus 6 meters, depending on the concentration. Of course, for general cases, what we use is the order of 10 to the power minus 6 meters, means micrometers is the width of this diffusion layer. And electric field between these two is nothing but equal to E equal to V by D separation. That we can calculate the value of the electric field. This is required for the neutrons. Next, the electrons, if they have to cross the junction, they cannot cross now, they should have enough energy that is done with the power of applying the battery potential difference here. If you apply the high voltage here and here, then electrons can cross across this. That we call as biasing, we will discuss next part of it. And here electrons have to cross the junction, means they should have enough energy. How much energy required is nothing but equal to E into dV not in electron volts we are discussing. Around 80 joules of energy. That means this dV is the potential difference and the electron charge is E. Then energy required from the electron to cross the junction is equal to dV. And for germanium, this barrier potential is in the order of 0.2 volts, and for silicon, the barrier potential is in the order of 0.6 volts to 0.7 volts. Sometimes they will give you as 0.7 volts. In your textbook, it is given as 0.6, but problem sometimes they will give 0.7 also. In the laboratory problem also, the practice will do with silicon diode that contains dV equal to 0.7 volts. So 0.65 to 0.7 can be there. So we have to remember 0.65 to 0.7 volts is for silicon. For germanium, low voltage is there, that is 0.3 volts. So what is the electron energy required to cross the junction of the barrier? Barrier is obstacle. Junction barrier is equal to energy required is 0.2 volts, means 0.3 electron volts required for the electrons to cross for germanium, and 0.7 means 0.7 electron volts energy required. 0.7 volts, 1 volt equal to 1 electron volt energy. So 0.65 volt, 0.7 volts means 0.7 electron volts energy required for the charges to cross the junction. Next circuit symbol for this diode is arrow mark. This arrow mark is indicate direction of conduction current that will pass the diode from P type to N type, P to A. And current will pass only when in the case when this A is higher potential, P plus N to minus current will pass. This arrow indicates the direction of conduction current. But this in the market or in the laboratory, what the diode shape you will find. Diode in the lab, what you find is one bar will be there. That is a rectangular bar, like cylindrical portion, cylindrical bar. Like this one will be there, and you find the band, one band on the diode. The band is always towards the N side. That is not the center, that is to the corner. And at the end we have the two wires connected. The wires are made of the copper for connecting the electrical circuits. Band indicates towards the north side, and towards the N side. The current is from P to N. The circuit symbol for diode is arrow mark with lines. This white part is P, other part is N. This arrow indicates direction of conduction current that can pass, and current doesn't pass in direction only when the voltage at A is greater than the voltage at P. Then only current passes from P to N. That indicates direction of conduction current, and the voltage is provided by the type of battery. That is called the bias. Next is the diode. What you find in the laboratory and in the shops, what you find is in this shape. This is a cylindrical shape, and one side you find the band, black band or color band. The band indicates a N-type material. It is not in the center, it is at one end. At the end points you have the connecting wires of metal copper. That is to make connections in the electrical circuits. And conductivity. Conductivity is given. Conductivity is the reciprocal form of resistivity. more resistivity, less conductivity and vice versa. So here for the conductivity of the semiconductor circuit, that is because of holes and as well as electrons. So total conductivity is because of the more conductivity, more charges can pass. Some of the conductivity is here to take up. And this mobility is how freely the charges are able to move is called as mobility. Mobility of the electrons is more than that of the holes. Holes cannot move freely. The electrons can only move freely from one atom to other atom. Holes can jump only from the in between also electron exist freely, but holes can exist only in the valence band, outermost orbit, and when electron occupies that place and this over is moving to other place. Otherwise, hole cannot move. But electrons can exist in between atoms also. Holes exist always with the atom in the covalent band outermost orbit. The mobility already we know before as a ratio of the drift velocity and electric field. This is not required for this topic. In this topic, what is required is this relation, and this relation also required only for the numerical purposes. That too only for NEET, not CET. NEET and JEE purpose only this formula is required. But mobility term, this can be asked for CET, which is easily free having more mobility and which is free to move is electrons, not holes. And holes are heavier. They behave as if they are more heavier than that of electrons. Next, the voltage versus distance graph, VR graph. Potential V is R graph. P is the voltage at the barrier. This is what talking here is at junction. Junction is a point where between the two P and N type material is a junction. So it is called the junction diamonds. At the junction only we are discussing these graphs. At the junction where the ionic region P type or N type. P type what we have is a negative ion crystal, and N type we have the positive charge. Means negative charges and positive charges. Electric field is from plus to minus. At the junction, because of this ion, this is the direction of electric field produced by these ionic regions. At the junction, P to N type. N type will have the higher potential and P type will have the lower potential. So the electrons have to pass through the barrier, they have to jump. The charges have to jump across these barriers, and this graph represents the potential variation with the distance r from center. Distance increases means the barrier width increases. For this, negative charges have to cross this side, positive charges cross this side. Next is volume charge density. Charge density is not uniform at the junction since the density changes from 0 to maximum and again 0 to maximum and again 0. Now repeating is not required, just know that charge density graph, this is also important for JEE and NEET. This graph is required for all cases also. Cases, JEE, NEET, all this is important and multiple times it was asked. And this graph is only for JEE and NEET, this formula also for JEE, NEET, and this electric field also JEE. This graph, this formula, this one is for JEE and NEET, but this is required for all exams. Next, the electric field and the potential derivation is E equal to minus dV by dr. This means direct potential. That is a differentiate, negative sign here. Because of the negative sign, we will take the negative sign graph here. Electric field comes in the graphical. P side we have the negative ions, N side we have the positive ions. R is the distance from center right side, and this is the left side. We take the relationship. The graphs also you have to do. Next part of the biasing of the PN junction diode. Biasing means showing partiality, giving inequality. Here every battery has a two potentials. One is higher potential, another is lower potential. At the potential, at an infinite potential is 0, plus or minus. So ground, with respect to ground, 0 potential. The plus terminal has higher potential and minus terminal has the lower potentials. Connected to the ground. So every battery has a two potentials, higher and lower potential. You connect the battery to the diode, but the diode also has a two type of materials. One is P type and N type. That giving unequal potentials for the P and N type material is called as a biasing. There are two types of the bias of the diode. One is called as a forward bias, another is called as a reverse bias. Forward bias, reverse bias. In the forward bias, if current passes through the diode. In reverse bias, current will not pass through the diode. It blocks it. So diode acts like a switch. It permits current only one direction when forward bias and try to stop the current in the reverse bias. What is forward bias? In the case of the forward bias, this is forward bias. This forward bias, P type battery is connected to the plus of the battery, N type is connected to the minus of the battery. P type to plus, N type to minus. And the junction parallelity. What happens in the case of the junction parallelity is decreases. The holes P plus repelled by the plus, so holes will cross junction towards the N type. and electron cross junction towards it because of the battery electricity is produced inside. This is a weak battery, and electrons will cross the junction. When electrons also cross the junction across in the opposite directions, current is produced. So what happens in this case is barrier electric potential decreases. In the VR graph, if you check out this graph, this is multiple times asked on one of the exams. The potential graph with the distance decreases, shifting towards the downwards. Next is where injecting value decrease. What about the forward resistance? Forward resistance is very low for the diode, and V equal to IR. Ohm's law, we can apply resistance equal to R equal to V by I. So forward resistance is nothing but equal to whatever the current is. Delta means indicating is that I2 minus I1. Changing the current we take corresponding change the voltage we take, the ratio is nothing but equal to resistance. Forward resistance is very low for the diode, and for ideal diode resistance supposed to be 0. Practically we don't have ideal diode, therefore we have the resistance in ohms, 10 ohms, 20 ohms, up to 100 ohms is possible for the forward bias resistance. Silicon diode has more resistance compared to that of the germanium diode. Holes and electrons cross junction opposite direction, then only current is passing in the circuit diagram in these directions, plus to minus. And current, but what current is always sum of the current, so what the current plus electric current inside this. But what about the outside? Outside holes cannot come. Holes are present only inside the semiconductor, not outside. Outside electrons only produce the current. Where holes are produced and they recombine, produce and recombine, the electrons disappear only inside the semiconductors. Holes not come out of the semiconductor. Next. Graph you check up, forward bias graph as the V increases. We take this voltage variable ones, and we can have the ammeter here to measure the current, and voltmeter connected to the junction, diodes is the voltmeters. Voltage across the diode is measured by applying the battery voltage and keeps on changing. At the junction barrier voltage, which is VB, what we told is VB is nothing but equal to 0.3 volts for germanium, and 0.7 volts and 0.65 to 0.7 volts for silicon. So the battery voltage should be more than this barrier potential, then only current passes through this. So battery voltage should be more than that. The battery voltage is less than this barrier potential, then current cannot pass across the junctions. So here if you plot the graph, the battery voltage is increased. The forward current first will not be there. Then it starts increasing by large values when the potential is 0.3 volts for silicon and 0.7 volts for 0.3 volts for germanium and 0.7 volts for silicon. This voltage, the current will be large. Before the current is very less. That will be milliamperes to ampere current depending on the type of the diode we are taking. This is called the forward bias. With the forward bias, current increases gradually to high values. Initially current will be 0 only when the voltage is less than VB. Small, very close to 0.7, the small leakage current will be there. That is the practical cases. Theoretical cases actually they should not be there. Directly from 0 and it rises to 5 volts. That is the ideal diode. Ideal diode will not be like this now. It will be straight from this point, but it is not a ohmic substance. Therefore, will not be I is not proportional to I in any cases. Next, reverse bias. In the reverse bias, what is happening is P type is connected to minus of the battery, N type is connected to plus of the battery. Reverse connections. P type to minus and N type to plus of the battery. This is called reverse bias. Junction barrier width increases. The width increases. How it can explain? Next, the resistance. Reverse bias resistance is very high, in the order of kiloohms to megaohms. For ideal diode, reverse resistance is infinity. Means current should not pass. Resistance high means current should not pass. What happens here in this case? Reverse bias current is supposed to be 0, and barrier potential width increases. In the diagram, it will be upward direction. Here increases, here also changes. But generally we discuss only this side because current electrical direction passing towards the N side. N side means we have the positive ions. Positive ions are there. Positive ions means the plus is supposed to minus side of the ionic regions. So higher potential will be present upwards. Lower potential present in the diagram is downwards. So what is happening here is plus to minus means these electrons will be labeled by the P2 minus N2 plus, reverse will connect, N2 plus, P2 minus, N2 plus, means electrons will be attracted towards this plus, these holes towards the minus. So electrons go away from the junction, holes go away from the junction. The result is electrons go away from the junction, holes go from the junction, is more ionic regions are formed. The width increases and the electron holes are not crossing the junction, therefore current will not be there. Current should not be there in the reverse bias. So current is supposed to be 0. Here the current is supposed to be 0. Supposed to be. But practically it is not zero. Why it is not zero? Very small current courses and remains almost constant after some time, and suddenly current increases to very large value. This is small current passing the reverse band of microamperes, so very small, negligible, very close to zero. Current should not pass. But why the current is also there is because of the minority carriers. In the p-type metal, what we have is holes are major carriers, n-type metal we have the electrons are major carriers. But in holes, because at high temperature, room temperatures, minority carriers are produced. Practically we take into the experiments at room temperature. So at the p-type metal we have the few electrons at the minority carriers, and the n-type metal we have few holes at the minority carriers. So what happens is that this is a plus minus. So this is a plus because it holes, minus because the electron they cross the junction. So these minority carriers cross the junction produce a current, but at a very few number. Therefore the current is very small. It will be zero, very close to zero microamperes. But it is not completely zero. It is very low voltage. But if you increase the voltage, what happens? If you keep on increasing the voltage, it's called the reverse voltage. We have the reverse bias voltage. Reverse bias voltage, battery voltage, we keep on increasing. Minus one indicates reverse directions. Increase, keep on increasing. Then what happens is that electrons and holes are being accelerated with high speed to high speed. Whenever they accelerate to high speed, this battery potential provides the electric field inside. The electric field makes the charges to accelerate. The acceleration of the charges is equal to E by m. E by m. Electrons minus n and holes plus. E value is same for electrons and holes. One is plus and minus. So they travel in opposite directions and they collide with the bonds, covalent bonds. When the voltage is very high, the acceleration is more. More voltage, more electric fields. And more electric field, more acceleration. More acceleration is more collision of the probability is there for the electrons with the bonds, and to that reason what happens is bonds break, more bonds break. More bonds break and the temperature increases with the friction and with the collisions. Temperature increases, temperature increases. When the temperature increases, more bonds break. So the when more bonds broken means more holes and electrons produced. The p-type and n-type means minority carriers number goes on increasing and they may become majority carriers. That is due to increase of temperature. So this increasing the charge carrier from minimum zero very low value to very large value is called as an avalanche breakdown. Avalanche breakdown indicates that avalanches are used for the ice. Due to the rigidation, when the ice is squeezed, that mass, that ice particles will stick to each other, and the small quantity of the ice and small stones drop from the top of the hill with the snow covered mountains. This small quantity, by rolling downwards, by the time it comes downwards, that becomes a very large quantity. As it rolls, it collects more and more snow and ice. By the time it comes to the ground, the quantity increases very large. Starting from small value increase to very large value, that is called as an avalanche. Breakdown is called as because the diode is breaking down. The big bonds inside, bonds are broken out, so it's called as an avalanche breakdown. And this avalanche breakdown, now diode also said to be broken down, and diode damage. Diode damage due to increasing temperatures. And the crystal structure will change, the diode will become continuously like conductor or like insulate also. Diode will not work anymore once the breakdown region is reached. Repeat once again. In the reverse bias, as the voltage is increased, the current will be initially very low and gradually increases. The low current is because of the minority carriers, so there is a P and n-type carrier. As the reverse voltage increases, there will be charge carriers, minority carriers will be accelerated and collide with the bonds. Covalent bonds breaking more bonds and increase the temperature. The increase of temperature breaks more bonds and minority charge carrier concentration goes on increasing, current increases for large bonds. So the current is on increase very large value, and after reaching a particular voltage, reverse voltage, the current will increases to so large that it will not be any control of the voltage. After reaching this breakdown voltage, the voltage is called the breakdown voltage. After once you reach the breakdown voltage, more maximum bonds are broken away and diode is damaged, and current is not in control of the voltage. This is because of minority carriers. Minority becoming major. That diode breakdown. The voltage is called the breakdown voltage, and the corresponding diode breakdown process is called as an avalanche breakdown. This happens because of the increase in temperature with the collision of the fast moving minority carriers, which becomes equal to majority carriers. And voltage will not increase beyond that limit because the diode will give you exactly. If you connect the voltage across this diode and if you increase the voltage in reverse bias to high values, after reaching the VR values, the voltage across the diode will not change. It remains constant, but current will be very large. Current will not be in any control of the battery voltage. And it is not only the diode is not only device, V is not proportional to I, whether it is forward bias or reverse bias. Next type of diode we are going to discuss is xenodiode. Xenodiode is not there in CET. It is not there in CET. It may be asked for a NEET and JEE, that I will discuss as an extra point for the JEE NEET. It is not in CET.